I'll tell you a little bit about eigenvalue interlacing, definition, what it is, some theorems about eigenvalue interlacing, a general theorem which is called Courant-Hilbert theorem, which applies to real and symmetric matrices, also to Hermitian matrices, but we'll just do it for real and symmetric matrices. And then we'll see applications to graph theory via two methods, one which is called Cauchy interlacing and one which is Hemmer's interlacing. And if we have time at the end, I'll show you a couple of examples, and in the afternoon we'll do more examples related to these methods. Okay. So I'll start with the definition. So today we'll talk about eigenvalue interlacing. First, what is interlacing? Assume that we have two numbers m and n, natural numbers, and n is the larger one. Okay. And then we'll have two sequences: a longer sequence of length n and a smaller sequence of. Assume that. Let me see how I. Okay, so theta 1 greater or equal to theta 2 greater or equal to theta n is a sequence of, is a set, well, let's say sequence of real numbers. Assume that, so I have this one, and let me write it this way, and mu1 greater or equal to mu2 greater or equal to mu m are two, let's say, collections of real numbers. So again, maybe I'll put it this way, n greater or equal to m, so that we have more thetas than we have mu's. We say that the sequence the sequence mu1, mu n, mu m interlaces theta 1, theta n if the following holds: if for every I from 1 to m, if I look at the if I look at the theta I entry in the big sequence, this is going to beat the corresponding I entry in the small sequence. But you have something which may seem a little bit weird. I'll show you an example in a second on the other side, and this is going to be greater or equal than theta I plus n minus m. So this is a general definition. Again, for us, these sequences are going to be eigenvalues of two matrices, but the definition is general. Anytime you have a sequence of real numbers, the sequence that have smaller number of members interlaces the other sequence if the numbers from the smaller sequence kind of go between the numbers of the bigger sequence. So let's do one example that hopefully will help you understand. Let me do it here. So let's see what happened in this definition if m equals n minus 1. Okay. Now, again, I will have, I hope this is not going to be too confusing. I have this sequence theta 1, theta n. Now I'm going to draw it on a line. And of course, if I draw it on the line, the order is the other way. So I have theta 1 here, and for my picture, let's assume for the picture that the thetas are distinct. So you have theta 1, theta 2, theta I plus 1, theta n minus 1, and so on. Okay? And now a sequence, so we will have now the other sequence. Let me put it below it. So mu1 greater or equal to mu2 greater or equal to mu n minus 1. And now let's just write first what the definitions say. So if we take, so in this situation, when m equals n minus 1, n minus m, which is this weird, this term a little bit here that may confuse you, this equals 1. So that inequality over there, this inequality, or inequalities, because they happen for every I, they translate into what? They translate into mu I. I'm going to change the order. I'm going to change the order now just to match what I have here. Less than or equal than theta I and greater or equal than theta I plus 1. Okay? So in this case, perhaps this is the most intuitive case where you can understand what happens for Eigenvalue interlacing. You have this bigger sequence, theta 1, theta n with n terms. You have a smaller sequence that has just one less element. You say that this sequence, the smaller sequence, interlaces the bigger sequence if these numbers from the smaller sequence go between the gaps, in the gaps between so basically your mu1 has to be here. You see, inequality here you see is not strict, is with less than or equal, so we'll see in a second that, you know, mu1 can happen to be theta 1, something like that. And then here, this is where mu I goes, and this is where mu n minus 1 goes. Okay? So this is the case where m equals n minus 1. Okay, so I hope this is clear for everyone what happens. It's just you have n numbers, you're going to have n minus 1 gaps between consecutive them. I mean, sometimes the gap will be, if theta 1 and theta 2 are the same, then when you have this interlacing, it's guaranteed that mu1 is going to have to be equal to them as well. Okay? Now, so this is this simplest case when m equals n minus 1. For the general case, what happens, this inequality stays the same, so the bigger matrix beats the small, or the ith is going to be the eigenvalue of a bigger matrix, but for now, the ith entry of the longer sequence beats the ith entry of the smaller sequence. But now what happens when you have n and m differing by more, you're not going to be able to put this mu I just in this interval theta I plus 1. It could be an interval theta I, theta something more here. That interval, it's a bit looser. Okay, so that's all it is. Okay, so in some sense, think about it. If n and m are close, you have kind of close control where the mu's go. Once the difference between n and m becomes larger, your interval in which this mu I can live, it's a little bit looser. Okay. If you have any questions, again, just feel free to ask. But this is a general definition of interlacing, and what we'll do is we'll show various instances in which eigenvalues of matrices, eigenvalues of a smaller matrix will interlace the eigenvalues of a bigger matrix. But this definition, we'll use it throughout today. Okay? So, okay, I'll leave the picture there and I'll erase here and I'll state the main theorem from which everything will be derived. Okay, so as before, this is a theorem that sometimes in the books you'll see it attributed to Courant-Hilbert. It works for Hermitian matrices, but we'll do it just for real and symmetric matrices because that's how we'll apply it. So as before, we have two numbers, m and n, like this. N is the bigger one. And now we'll have one matrix. Let A be a matrix with real entries, which is symmetric. And we will denote its eigenvalues accordingly to, we'll have with eigenvalues theta 1 greater or equal to theta 2 greater or equal to theta n. Okay. And for us, we'll need the notation for, we'll need a basis of, an orthonormal basis of eigenvectors So I will write it here. So this matrix with eigenvalues and corresponding orthonormal basis of eigenvectors u1, u2, un. Okay. So this is our big matrix, and for us, in the situations when we'll apply it to graph, this will be adjacency matrix or Laplacian matrix. Most of the application I'll give you today will be adjacency matrix, so just keep that in mind. Okay, now we need a smaller matrix. To do that, let's assume that S is a tall matrix, so it's N and M, such that its columns, the columns of S are orthonormal. So that one you can write it that S transpose S equals identity M. Okay? So the picture will be like this. I have, this is A, which is N by N. This is one actor in our story. So this is going to be one actor. And now we're going to have a smaller matrix. And that smaller matrix, we will make it from this S and from A. And that smaller matrix will be like this. You will take, let me see, the other way around. The other way around. So we'll have S transpose okay, so assume that S is like this and denote B S transpose AS. Okay, so now because S is N and M, S transpose is, you can see from this picture, so this is M, this is N, and M. So this matrix will be a smaller matrix. And now we need to denote its eigenvalues by something. Denote the eigenvalues of B by mu1 greater or equal to mu m. And because A is symmetric, this matrix B will also be symmetric. And so we have an orthonormal basis of eigenvectors, so we'll use one of them. You can have many of them with an orthonormal basis. Orthonormal. Eigenvectors. Let's call it V. V1. Give me 2. V2. Okay. So I'll give you, this theorem has several points, including analyzing something about equality case. So I'll do first just the eigenvalue interlacing part without analyzing the equality case, and then we'll do the one a bit later. So, okay, so you have big matrix. So from it you make, with this S, you make a smaller matrix. So you have now two symmetric matrices, and now, because I kind of prepared you for it, surprise, surprise, guess what's going to happen, okay? So what will happen is that the eigenvalues of the smaller matrix, so the eigenvalues. So this theorem, like I said, has several parts. I'll just give you the first part now, and then I need some definitions for the remaining part. But the key thing is this first part that I'm showing you here. The eigenvalues of B interlace the eigenvalues of A. Okay. Any questions so far about anything that's? it's a little bit abstract and it kind of falls, you know, in front of you on a rainy morning, so it maybe takes a bit of time to get used to it. But like I said, if you want to keep something guiding you about, you know, what we're doing here, for us, this A will, like I said, today will be adjacency matrix of a graph, and that's how we'll apply it. That's how we're thinking about it. Okay. All right. So let me give you the proof. So what I will prove first, the key thing is to prove the following. So I'll take I from 1 to m, and we will prove that the ith eigenvalue in the big matrix beats the ith eigenvalue in the smaller matrix. And I claim that that's the only thing you actually need to know. Because the other inequality, remember, like, so this eigenvalue interlacing means that for any I, let me write it here, from 1 to m, what do we have? Mu I is less than or equal than theta I, and is greater or equal than theta I plus n minus m. So you can, I will give you the proof of this inequality. And then I'll show you that if you know that this is true, you can do a simple trick. Just multiply the matrix by -1 or something like that, and you can get this one for free immediately. Or you can mimic the proof that I will give you now for this part. You can mimic, actually that's probably a good exercise for you to do, just so that you understand what I'm doing today in this proof. Okay? So I'll just prove this part, and I'm telling you that, you know, once I prove this part, this other part, you have two ways of doing it. The easy way with applying this inequality to the negative of A and seeing how things work, or just repeating the proof that I gave here, but with not quite word by word. You have to change a few things. So here we will prove that mu I is going to be less than or equal than theta I. Okay, so let me, say, I will make it like this, theta I, just so that hopefully you'll remember what I will do. Essentially, this proof will be by finding some kind of double agent here, as before, which will be greater or equal than this, and which will be less than or equal to this. Okay, so that will be the trick of the key idea of the proof. Okay? So that's what we're trying to do. Okay. All right, so now let's denote some things. So first we look at, again, from our, the previous max, min, max, all that business, we look at mu I, and we want to show mu I is less than or equal to something. If we remember what we, when you look at this, so let me, when you look at the sequence mu1 greater or equal to mu I greater or equal to mu m, remember that we had to think about mu I from two perspectives, especially like mu1, it's always the max of something, mu m, they're always the mean. So there's no, you know, nothing to talk here. But mu I here, you can look at it from two perspectives. Mu I is the smallest from the beginning, and it's the largest from the end. So if you want to show that mu I is the smallest than something, you kind of have to look from the perspective of what happens on this side. Okay, so that's exactly what we'll do. So so I need just some notation. The first one is pretty easy. I think we've used it before. So denote by Vi the span of V1 Vi. So it's a span on the first part where lambda I is the smallest Rayleigh quotient. Okay. So this space is going to basically will allow us mu I will need this to you know, we'll need this space to get to lambda I. But now we have to have a connection between the two eigenvalues via some kind of intermediate this double agent that I talked to you about. So now I will define something that at the first glance is going to be a little bit scary, so denote by Wi V. So here, if I wanted to write it in, I'll write it like this. This is span of V1 Vi, okay? And maybe let's keep it here so we remember it. Wi, it's the span of V1 Vi. And now I will, this is Vi, sorry, Vi. And now I will need this Wi. So the Wi will be the following. So this is the orthogonal complement of the span of the following vectors. Let me think how it is. S transpose. Yeah. S transpose U1, S transpose Ui minus 1. When you first see like how, you know, who can come up with something like this? Well, they can come, you know, people like that can come up with something like this. You can come up with something like this for the other inequality, okay? So let's write it here. So this will be the span of S transpose U1, S transpose Ui minus 1, and we take the orthogonal complement of it. So for now, let's just do small steps, okay? So we'll get to Wi when we have to get to Wi, which is in 1 minute. But first, Vi. What can you say from the definition? What's the dimension of Vi? I, okay? So because the V's are orthonormal basis, so we have that dimension of Vi is I. Now, I would like to say something about the dimension of Wi. Doesn't have to be super precise, but let's start, before we go to the orthogonal complement, let's start with the span of this. Okay? How many vectors do I have here in this set? I minus 1. So before you do anything, you know for sure that the dimension of that span is going to be less than or equal to I minus 1. You don't know for sure it's going to be equal, but let's say less than or equal. You won't need anything else. So if the dimension of what's inside is less than or equal than I minus 1, then the dimension of the orthogonal complement must be? Yes, exactly n minus I plus 1. And now you can kind of get an idea, because we've done these things with dimensions before in another context. You get an idea kind of where this is heading. Okay? Dimension of this is I, dimension of this is at least n minus I plus 1. So if you add up the dimensions, you're going to get at least n plus 1. So you will be guaranteed what? Intersection is non-trivial. Okay? So let's just write that down. So therefore, dimension of Vi intersect Wi equals the dimension of Vi plus dimension of Wi minus the dimension of their sum. And then this is going to be greater or equal. I mean, here I have I plus n minus I plus 1. This dimension is at most n, so it's going to be greater or equal to minus n, and this will be 1. Yes, question? Yeah.
Explain again this dimension of Wi, because S transpose Ui has m components.
Just a second.
This is an n plus n.
So S transpose, yeah, so the U's are tall vectors. So S transpose is a long matrix, and the U is also going to be like the U1, for example, would be a, so you see you take rows here, you take this, so this will be this is S transpose U1. So both of these spaces, they are in which dimension? In which of what they're both in Rm. Okay, did I make what am I? Let me see, because I made a mess here. This couldn't be. Okay, so let me. Yeah. I think let me see if I got them mixed up. Just a second. I might have gotten the spaces mixed up. Okay. So. Just 1 second. What did I? A is theta. B is mu.
So the span of
Which one? Yeah, but I
so those V's are eigenvectors of B.
The V's. Yes, the V's are of B. But what did I mess up here? Yeah. So I think I just messed up the dimension here. Yeah, this is probably M. Yeah, sorry. That's all. Thank you. Okay. So these are the V's. They come from the matrix B, which is in M. So this is in Rm. And here the U's are tall, but this is also in Rm. Okay. Yeah, thank you. Very good. Okay. So again, here what we get is this dimension is at least 1. Hence, there is some vector. Let me see how I call it. Si, which belongs to Vi intersect Wi, and Si is not going to be 0. Okay. So this Si is going to play the role of double agent here. So this Si we'll try to play it because it's in 2 subspaces. We're going to try to get information from each of those subspaces, some inequality. Okay. Okay. Let me erase here. Okay, first the easy part. So we have Si belongs to Vi. Vi was the span of the vectors V1, V2, Vi. So obviously also Si is not 0. What does it imply about, so these were the vectors corresponding to mu1 greater or equal to mu I. So what's going to be the relation between mu I and Si transpose B Si, the Rayleigh quotient here? Less than or equal. So okay, so that part again, this is the thing that we did for, I think I showed you for largest eigenvalue, but you can do the same thing because Si is in here. You write it as a linear combination of these vectors. You plug it into here, you'll get a convex combination of the eigenvalues from mu1 to mu I. Mu I is the smallest, so that convex combination will be greater or equal than mu I. Okay? Now here, let's just see a little bit if we can. Again, it's a double agent, so this is one side of the story. Now let's see, obviously you would like to continue this and get on the other side that this is less than or equal than theta I. Now B had a formula, this formula, so you have SI transpose, S transpose AS SI divided by SI transpose SI. So now, you see this place here is where everything switches from B is going to switch to A. It's a different vector. Here, this is a Rayleigh quotient for B with SI. This will be a Rayleigh quotient. It doesn't look like it now, but it will be a Rayleigh quotient for the matrix A with a different vector. Now, from the top, you kind of see what the vector is going to be. So you can write this as SI transpose A SSI. Now, at the bottom, you have something like this, which maybe doesn't look like the inner product of these two, but maybe it does, because what did you know about S? S transpose S is identity. This is the place, okay? So this thing, so let me write it here, SI transpose SI will equal, you can do SI transpose S transpose S SI, because this one is identity, and then it's the same thing as SI transpose SSI. So that's what I'll write it here. Okay. Now we're not done. We're almost there. We have mu I. We relate it to this Rayleigh quotient of this vector SI. We switch from B to A. We got to a Rayleigh quotient of something. But now I have to, in order to say something about this Rayleigh quotient, I need to understand where this SSI, where does it live? And now we have to, here, you see here, we've used the part that SI belongs to VI. But SI also belongs to WI, and we haven't used that yet. So WI is the weird thing there. Okay, so let's use that. So I'll do it here. Because SI belongs to WI, what do we get? So WI is an orthogonal complement of something. So if you're an orthogonal complement of something, you must be perpendicular to everything in that something. So you must be perpendicular on all the vectors in the span, which you have them there. So it means that SI transpose, let's say S transpose S1 equals all the way to SI transpose S transpose S1 equals 0. Because you have to look, see, like the WI is the span of these I minus 1 vectors. So then, because SI is in here, it has to be perpendicular on all of them. And again, it's real and symmetric, so I can just write the inner product like that. So we have this, which means now, here I have this vector. So I will transform this part in terms of that vector, which is the same as SSI transpose S1 SSI transpose, here this should be SI minus 1, sorry. Yes, thank you. U, thank you, U. U1, UI minus 1. Thank you. So what does this mean? This is the same as S, this vector, belonging to what? You can say two ways. It belongs to the orthogonal complement of U1, UI minus 1, like this. But because you have a whole basis there that I erased it, U1 all the way to UN, you know exactly, you can rephrase this as the span of UI all the way to UN. So by this this kind of little bit piece of magic, at the same time you have something, you have one vector which is SI, which belongs to the span of these things from the beginning, and then you do something to that SI, and you have a vector which belongs to here. And okay, so now the U's are eigenvectors for A, and by the same argument as before, this implies what can you say now about this, the Rayleigh quotient SSI transpose A, SSI transpose divided by transpose here, and theta I. Which one wins on this side? Less than right. So this Rayleigh quotient is a very important thing because it allows you to relate these eigenvalues to each other. And in this situation, again, this is a little bit of a to me, it still feels an amazing, it's an amazing result because you can, like I said, you can have this double agent SI. So you have here SI transpose B SI, and then you switch from B to A, and somehow things are, you have a different perspective. So maybe erase there. This is the what is it? Bit of a magic. So one side, this side. So okay. So that's the proof. Yeah, I hope I didn't make any other typos through in the proof. Does anybody have any questions? Again, see, I've gone through this. I've taught this type of theorem several times to my students, and it's still like the details are a bit technical. So don't feel intimidated by it at the beginning. I mean, the only way you remember this, you have to write and rewrite the proofs a few times. So that's why I would suggest you do the exercise number. I thought we already had 19. 90? No. That's a new record. Okay, exercise 19. Prove that theta I plus n minus m less than or equal than mu I. 20. He's trying to get out of doing exercises, so he's giving smaller numbers. So, okay. So try to, like I said, I mean, both proofs will be straightforward. One is just mimic this proof, and I think that's useful for you to do so that it will help you understand this proof better. Because here you just have to pick up the right subspaces. And again, if you're troubled by how to do it, think about again from this perspective of mu I. Mu I greater or equal to something that will allow you to choose the subspace there from I going down, and then you need to, again, to choose a subspace, to choose what you do here, think about dimensions and think about a little bit how we did there. Again, like I said, that's the proof kind of mimicking this proof. And then there's the easier proof, like I said, the shorter proof, where you just apply the theorem that we just proved. You apply it to, if I have A and B, you replace you apply it to minus A and minus B. And when you change the order, the indices will change in the way you want it. So it will work out. Okay. All right. So let me see. Okay. So this is the first part of the theorem. In order to tell you about so I will erase and just write it on the board, and then I'll tell you about something related to equality case. So let's just maybe keep it here. So again, A what did we have? We had U1 here, U2, UN, then S, so A is a big matrix, S is S transpose S is IM, and then you have we have from it we have B, which is this matrix, and B will have eigenvalues mu1, mu I, mu m, and v1, vi, vm. And the main result here is again that mu I is going to be less than or equal than theta I, greater or equal than theta I plus n minus n for any I. Okay? Now I'll give you a definition. So here it may happen that you have equalities in these inequalities because they're not strict. And if you have equalities in pretty much all of them, you have something called interlacing is tight. So we say, so I'll just apply it for a general definition of mu and theta, mu interlacing theta. So we say that the interlacing is tight if there is some number, let's call it L, such that mu I equals theta I for I from 1 to L, and mu I equals theta I plus n minus 1 for I from L plus 1 to M. So if you had the theta 1, theta 2, theta I plus 1, theta n, and so on. So mu I will hit here, mu1, mu2 will be so the first mu's will be as large as possible. So this will be your mu i's. And after that, as you go down, so this one you kind of look from the back end towards. So here, if I have I equals m, mu m equals theta n. So this is here, this is where I will have mu m. When I have here theta n minus 1, this is where I will have mu m minus 1. And then you figure out what should be for mu L plus 1. So what theta should be here? Theta of, just plug it in. Okay, so on the first on the top, the mu's are as large as possible. On the other side, at some point it switches, and on the other side, all of the mu's are as you know, like as small as possible. Because you see, like our inequality is this one. It's always guaranteed. So when you start from the top, from 1, 2, up to L, the mu I achieves its potential. It's as high as it can be. But when you look from the end, when you look from the m all the way to L plus 1, this mu I will be here. Okay. So. Now this is not super important now. It will come up into play a little bit later, but for now, just yeah, just write it down and okay. So like I said, the Courant-Hilbert theorem has other parts. So you have second part, and I erased on the board, we had this thing with the double agent. You know, the double agent plays the theta I versus the mu I. Well, you can ask yourself, what happens if you have equality? If you want to analyze something about interlacing tight, first you can want to understand what happens if mu I actually equals theta I. And you have that, I wrote it in the corner there, you have theta I, you have this Rayleigh quotient in between them, and then you have mu I. So it's if the walls are tight, so the theta I equals mu I means everybody has to be equal there. So that's what I say. If mu I equals theta I for some I, then B has some eigenvector. That eigenvector will be that SI there. So, but for now we'll just call it differently. Let's call it V, such that SV is an eigenvector of A. So if you go look through that proof, if you have equality in, look through your notes, if you have equality in theta I equals mu I, then those Rayleigh quotients have to equal both eigenvalues. And you have the Rayleigh quotient, you had that vector SI coming from the space V1 all the way to Vi, so in order the Rayleigh quotient of it to equal mu I, it has to be an eigenvector. And then on the other side, it also has to happen that S times that vector has to be an eigenvector for A. So that's exactly what this is saying. So do we make it exercise so that low-hanging fruit? Okay, now you remember the number. Exercise 21, very good. Okay, and then, so there's another part 3. Okay, let's write the, okay, I'll just put 3 the following. If the interlacing is tight, so if you have interlacing is tight, then what you will have something of this form. AS equals SP. So this is you know, you have to be careful when you're dealing with this matrices. We know that this is the case, and you know that S transpose S is IM, but I cannot just make this S transpose from here, move to the left, and get this in general. But if the interlacing is tight, it's actually, I'm not doing that, but you can actually show that this is the case. And you can use to do that, okay? So if you have interlacing is tight, you have a closer connection, you have a stronger connection between A and B than this, okay? So clearly this implies this, but this doesn't imply this, okay? Yes?
We have some eigenvectors corresponding to the eigenvalue lambda.
Yeah, yes, very good. So this eigenvector corresponding, very good, to mu I, such that SV is an eigenvector of A corresponding to the same eigenvalue, but to theta I. But theta I and mu I are the same. Okay, so there's a close connection. We've kind of seen this type of thing. This is a bit different, more general, but we've seen something in this equitable partition business, but okay, so, okay. All right, so this is a general theorem, and now let me show you two applications for graph theory. Okay, that's what we want to do. Yes?
Do you have an explanation of like what actually this S matrix is doing to the A matrix in terms of the column space of the A matrix?
Which one?
Like B equal to S transpose A. So how is I'm asking in terms of the column space of A and
Well, I mean, what does this do when you multiply A by a matrix to the right?
not even in the tight case, but also the other case also.
So let's see it for the graph theory case. So then you will see like maybe like something concrete. Because here it's for the matrices, it may be a little bit, you know, it may be a little bit. But let's see for the graphs, and you can see what happens there. Okay, so the first application, so consequences or applications. This is called Cauchy interlacing. And it says the following, let A be, again, it applies to Hermitian matrices, but for us we'll just need the real and symmetric. Symmetric matrix, be a symmetric matrix. Now, Professor Kanan recalled to you the notion of principal submatrix and so on. So so principal submatrix, you just delete some rows and you delete the same column, the corresponding columns. So what happens is the eigenvalues of any principal submatrix of A interlace the eigenvalues of A. Equivalently, if you have any real and symmetric matrix, you delete some rows, you delete the same columns. Obviously, the matrix you get is also real and symmetric. It has real eigenvalues. So the eigenvalues, so in this case, your A is this, and maybe the simplest case you can think about the B is you delete the first row and the first column. Okay? Of course, if you, depending on the situation, you may want to delete more. But this is, okay, again, this is a general theorem for, like I said, it's true for Hermitian matrices. Here we go to real and symmetric, and then we'll do one more step. We'll go for graphs to tell you what it means for graphs. Okay? So, so eigenvalue interlacing for graphs. So Cauchy. So this is, I'll do it just for the adjacency matrix. Let gamma be a graph. If gamma prime is an induced, so this is the keyword, induced subgraph of gamma, then the eigenvalues of the adjacency matrix of gamma prime interlace the eigenvalues of the adjacency matrix of gamma. Okay, so it's clear how this implies this, because an induced subgraph, the easiest way to remember what's an induced subgraph is, so it's a subgraph which is obtained from the original graph by deleting some vertices, possibly none. So you just delete vertices, you leave all the edges intact. I mean, obviously if you delete a vertex, you delete those edges, but the other ones you leave them the same. So it's important to know the distinction, and here this is very important, that when you apply Cauchy interlacing for graph, it has to be an induced. Or if you take this, so you have to be careful. Professor Canano will talk about Laplacian matrix later. So if you try to apply something to Laplacian matrix, you have to be careful, because if I have a Laplacian matrix, I have those things on the diagonal, which are the degrees. So if I take a principal submatrix of the Laplacian, I can apply Cauchy interlacing, it's okay. But if I take an induced subgraph of the graph, the Laplacian of it is not going to, very likely is not going to be the principal submatrix of the Laplacian of the big graph, because those degrees will be messed up. Okay? Now, so it should be clear how this implies this. Now, how does this imply this? Because here, this is general, this is S something. So maybe I'll change the picture. Let me see how. So let's say I like the first row and first column now. I want to delete the last row and the last column, or something. Yeah. So you can have B, and maybe you want to delete more, something like that. So here you have your A. You don't have a B, but to get a B, you need an S. So let's say my principal submatrix, it's something like this, like on the first, what did I use? Let's say this is on the first M and M. Okay, for simplicity, I can assume that. So I do that by using the matrix S, which is N by M. And here you put identity matrix on the first M rows, and then you put the zero matrix N minus M. So this is kind of if you want a matrix whose columns are orthonormal, this is maybe the first thing that you're gonna think about. You know, like the canonical vectors. You know, these are the basis vectors if you look down. And then if you apply S transpose AS, this kills off all these rows. So yeah, do it, and then you get this principal submatrix. Okay. So Cauchy interlacing. I mean, there are different proofs of Cauchy interlacing. If you look in the book by Gottsill and Royal, they give more like an analytical something with power series and functions, poles of functions, and so on. You can read that proof. It's a little bit different than what is here. But here, Cauchy interlacing just falls from this big theorem. Good? Okay. So that is one, okay, for graphs. And then for the second one is called Hammer's interlacing. And for this Hammer's interlacing, so this is one. I mean, Hammers didn't call it that, but he obtained this in his, so this is Wilhelm Hammers in his PhD thesis, 1978. But if you want a very good like overview of it, it's not so recent, but it contains more examples than I'll give you here this week. You can look of, he has a paper in LAA, interlacing, I think it's called Interlacing and Graphs. I think you can find it online, and it has a lot of examples of applying the Hammer's interlacing, which I haven't told you what it is. Okay, so let me tell you what it is. Now, here, do not confuse what I'll tell you with the equitable partition stuff that we talked about yesterday, because there are some things that will be similar, like a partition, we'll talk about partitions and so on. But the partitions that I'll talk about here, they don't have to be equitable. They may happen to be, but they're general partitions, okay? So, okay, so let me define something also called quotient matrix, but here's how we're going to define. So assume, again, we have a graph. Assume that V, we have, again, pi. Let me change the, I don't want K, I will put M. Let's say this V1, Vm is a partition of V. So V1, V2, Vm. Let me do it, so yeah, obviously that's my general graph. Let me do it on a particular graph here. Let's take our favorite graph, this one. And let me take this partition to be something simple. This triangle, this is V1. Yeah, that's, no, I don't want that, because it will be equitable. Let me take this part to be V1, and these two vertices on this side to be V2. Okay? So now, for any partition, you can define, so you can define, we define the quotient matrix. Let me call it B, which is B of pi, associated with pi, as follows. So this will be Bij as before, I and j from 1 to m, associated. So what do we have? We have a Vi here, we have a Vj here. Now, in equitable partition, everybody in Vi had the same number of neighbors here. Here, it may not happen. You can have some vertex has 2, some vertex has 1, some vertex has none. Okay? So I will define Bij as the average of the number of neighbors of a vertex from here that live in here. The other way to look at it is you count the number of edges. Count the number of edges between Vi and Vj. Let's call it EVI Vj. And you divide by the cardinality of Vi. Okay? So this Bij is EVI Vj divided by cardinality of Vi. Because again, in between these two parts, what's the number of edges? It's the sum of the neighbors of the vertices in here, neighbors that live in here. And then you average by the number of vertices that live in here, which is cardinality of VI. Okay? So let's just do this example here. I'm sorry for messing up. Let me draw a different picture so that you can see. Let's see. So this is V1, and this is V2. So what will be the matrix here? The same thing as before. If Vi and Vj, so the same thing as before. If Vi and Vj are the same, then Vi, it counts the number of edges twice. So on the diagonal entries, you get the average degree inside Vi. So here, V1, you have here, this vertex has degree 2, this vertex has degree, the average degree inside here. So this vertex has degree 1 here, degree 1 here, degree 2 here. So this is going to be 4/3. And then you count, you're going to divide by 3 because you have 3 vertices in here. And like I said, the simplest way, you could take each vertex individually and add up the degrees, but you can just count the number of edges in between. So you have 1, 2, 3, 4. So it just happened to be 4/3. Backwards from here, in V2 we have 2 vertices, and we already calculated that we have 4 edges, so it's 4 over there. And inside here we have 0.
But then counting edge first component will be
Which one?
first entry.
4, 3?
Choose edge counting. First entry will not come 4/3. 2/3 will come.
Here?
Counting edge divided by.
Yeah, so you look inside here, and inside V1 you just have these 2 edges. So the sum of the degree will be 2 times 2, which is 4. And you divide by the number of vertices. So here I said if Vi and Vj are the same, then this will, what I'll do here, it will be twice the number of edges. We'll count each edge twice. Okay? So essentially you count for general I and J, you will always count the average number of neighbors. It's of the vertices, so you take all the vertices in Vi. For each of them you count how many neighbors they have in Vj, and you average. Now if Vi and Vj are the same, it means that I look at every vertex in Vi. So here I have 1, 2, 3 vertices in V1. How many, what's the degree of each vertex inside V1? Well, this vertex here in the big graph has degree 2, but inside V1 has degree 1. This vertex has degree 2 here. It has 4 in general, but 2 in. And this one also has degree 1. So if I sum up, 1 plus 2 plus 1 is 4 divided by 3. Make sense? Yeah. Okay. So this matrix is not going to be, obviously you see, is not going to be as nice as integers for quotient matrices and so on. You get like some weird numbers. Okay. Now, let me state you the result. So I'll erase here. And you saw the example, like this matrix is not even, it's not even symmetric. Now what will happen is 1, the eigenvalues, so this will be kind of understood, but B, even though it's not symmetric, will show that it's similar to a symmetric matrix. So B will have real eigenvalues. So the eigenvalues of B interlace the eigenvalues of A. So the game here, the way you should think about it is, you have some kind of structure in your graph. You have some kind of combinatorial parameter that you're looking for. So that imposes some kind of constraint on the structure of your graph. So based on that, you partition your graph into some parts. We'll show some example in a second, like 2 parts, something simple, but sometimes it could be more parts. Now, what will happen is this B will contain in it some information about that combinatorial parameter that you're looking for. It will contain something about combinatorial properties that you're searching for. And then ideally B is small enough, easy enough that you can calculate its eigenvalues relatively easily, okay? And then what you can do is, by this interlacing, you relate this B, which will carry some kind of, B is a matrix, so its eigenvalues are spectral things, but they will carry some kind of information about the structure of the graph, and you will relate it to the eigenvalues of the B graph. So that's kind of the gist of it. And I forgot to say that that's the same thing with Cauchy interlacing, okay? Okay, so that's, okay. Now, here's the second part. If the eigenvalue interlacing is tight, which is this definition that I gave you here, then you can say that the partition that you have is equitable. Then the partition yes. Well, you know for sure that if the partition is equitable, you know that your eigenvalues from that quotient matrix will be eigenvalues of the big thing. I don't know off the top of my head if you can tell that they line up the way you want it. You know, like as for to have interlacing tight, you need these eigenvalues to line up, you know, the way you want it. Yeah. So, but yeah. Okay. So let me give you one examples for each situation. We'll do some more later in the class, but then we can stop. So I have Hammer's interlacing, Cauchy interlacing. Let me erase it. Okay. So again, another application examples. So this one is called, this is for independence number. Do I need to give the definition? Does everybody know what an independence number is? No? Okay. No or yes? No? Okay. So again, let gamma be a graph. An independent set. Well, let's this. We say that S, a subset of V, is an independent set. Of gamma. So it's an independent set if there are no edges with both endpoints in S. Okay? If gamma has no edges with both endpoints in S. So this is our graph. Independent set, this one. So this is an independent set. You see, because these three fat vertices, there are no edges between them, okay? Now, the independence number of a graph alpha gamma of gamma is defined as the maximum size of an independent set of gamma. So alpha of gamma is the max of the cardinality of S as independent set. Okay, so just because I gave you an independent set here, you check that it's independent set. So this picture, it doesn't tell me that alpha of this graph is 3, because this is a maximum. So when you give me an independent set and you verify that it's independent set, you just give me a lower bound. You just say, this picture tells me that alpha of gamma is greater or equal to 3. How can you, is this the right? Is alpha equal to 3? You can see if you can find something with 4, okay? But even if you find something with 4, the question is the independent set with 4 vertices, is that the largest size that you can find? So again, for this independence number, so alpha of gamma, if you want to find lower bounds, those are, you can just try to do by examples. Or sometimes there are things like probabilistic method in which people try to prove things by existing, show that something exists. So you have to, if you want to prove that alpha is greater or equal to t, you have to convince me that there is an independent set in your graph which has t vertices. You either just give it to me like on the picture, hey, 3, or give me a proof or something for a modular. Now, what do you do here? So when you're trying to find this independent set, you'll try to find it exactly. And in general, this is a difficult problem computationally, like there's all this complexity theory about it, but you like to find something, okay, how do I find an upper bound for the independence number? Well, you can say, well, I'm going to take an independent set S, and somehow I will require a proof. I will prove that the cardinality of it is at most this much. So here, it doesn't work by example. Here you have to prove something, okay? So that's what I will give you now some places where you can get an upper bound by proving something. Okay. Okay, so let me give you an upper bound for the independence. So this is called Cvetkovic inertia bound, because it has something to do with the number of positive, negative eigenvalues. So what it says is that if gamma is a graph with n vertices, then the independence number of gamma is going to be less than or equal. I'll write this in 2 ways. It's the minimum of n minus n plus and n minus n minus, where n plus is the number of positive eigenvalues of A, and n minus is the number of negative eigenvalues. And so the A is the adjacency matrix. So A has positive, negative, and also 0 eigenvalues. Okay? So So A is the adjacency matrix of gamma, and when you look at its eigenvalues, let's say 0 is here, so everything from here to here, if you count, you will get m plus. If you have something here, obviously at 0, you will count n0 because 0 may have a multiplicity, okay? And then from here to here, you will have n minus. So this is maybe theta 1. You go here to some kind of theta, I don't know. This is theta n. Okay? And so n, my n, it's the n minus, n0, and n plus. So you can rephrase this, if you don't like it, n minus, n plus, plus n minus, you can write it n0 plus the minimum of, because n minus, n plus, this is the same thing as n0 plus n minus. N minus, n minus is n0 plus n plus. So you can write it like this. But either way, so alpha of gamma gives you an upper bound. Maybe this is the easiest because let's say n minus n minus. How can you say it in words? It is the number of eigenvalues of which are non-negative, yes. So this is the number of eigenvalues. So I'll change it here for lambda because we have lambda when we have this. Eigenvalues of A that are non-negative. Okay, so let me, how did he prove this? So the proof is very simple. What you have is so assume that M is the independence number. You have to denote it by something. And consider an independent set with cardinality of S is M. So you have M vertices such that no two of them are adjacent to each other. Now, what do you think about, what can you say about the principal submatrix of the graph which corresponds to the vertices in S? It's a zero matrix. So without loss of generality, I can assume that A looks like this. That this S, the vertices in S are at the beginning, and I have here just a giant 0. Okay? Okay, so the B matrix for me will be this. This is my principal submatrix, which, you know, this is the easiest case because you can calculate. You know the eigenvalues. Okay? So what does Cauchy interlacing tell you? Something. So you have to write down what Cauchy interlacing tells you. So from Cauchy, you can get that lambda, the mth largest eigenvalue of my graph, is greater or equal than the mth largest eigenvalue of B. What is the mth largest eigenvalue of B? 0. Okay? So then let's do a picture. Let me erase it. So you have 0 here, lambda n is somewhere here. So we're trying to place this. So lambda m a is somewhere here. It's kind of, you know, it could be here, but it could be in the, you know, 0, okay? Now the other thing that you will get is you look on the other side. So remember, our interlacing was something like mu I less than or equal than theta I. And this is what we used already. But you also have something of the form mu I equals theta I plus n minus m. And here, it makes sense to go to the first one. So let me write this so this will be lambda I of b less than or equal than lambda I of a greater or equal than lambda I plus n minus m of a. We use this, what do you use it, at m? So we use this I equals m. And we will use this one at I equals 1. So if you take I equals 1, you know this is 0. So 0 is going to be greater or equal than lambda 1 plus n minus ma. So lambda m is there, and lambda n minus m plus 1a is here, somewhere here. Now, so lambda m is here, so it means that A has at least how many non-negative eigenvalues? At least m, because lambda m is greater or equal to 0. It's at least m non-negative. But what was the precise number of non-negative eigenvalues? N minus? N minus, N minus. So because the total number of, let me erase here. So this tells me that N minus N minus is greater or equal to M. It kind of just falls into your lap because of this. Okay. Now, what do you think happens on the other side? Lambda n minus m plus 1. So if you count from back, this is n, this is you count, this would be the first from the back. This is going to be the mth from the back. So it's the same argument. So A has at least m non-positive eigenvalue. And you get n minus n m plus is greater or equal to m. And that's exactly this. Okay? So it's a bit weird to think about it this way, but in this situation you see what are you looking for? Independent set. What's an independent set in terms of linear algebra? It's the same thing as a principal submatrix, which is all 0. Okay, what do I know about principal matrices? Cauchy interlacing. What does that mean in terms of, it means this. It means an upper bound and so on. So I'll stop here, and we will do in the afternoon, we'll do applications of Hammer interlacing, and I'll show you examples where we can apply this inequality for like some simple graphs like Peterson graph and so on, and we'll see how it works. Okay, so do I have more time, or is I finished?